for delivering the second lecture for day 2 of this ongoing 5-day GAN course. The title of his talk for this lecture is Theory and Technology of Antenna and Propagation for WPT. Over to you, Professor Naoki.
Thank you. I have so good morning again. I'd like to start the second day of the GN course. And yesterday, I mentioned we can classify the wireless power transfer system into these 3 stages. So beam wave propagation and circuit technology. Today, mainly, I explain the WPT beaming technology. First lecture here, I'd like to introduce how to increase the beam efficiency by the antenna. And in the afternoon, I'll explain the phased array antenna technology, because now I would like to introduce how to increase the beam efficiency, but user moves somewhere. Beam efficiency suddenly decreases. So we must control the beam direction. It's a second lecture today. And third lecture today, I'd like to introduce how to detect the target position. Because even if we have a good beam control technology, there is no meaning if we don't know where the target is. So Tuesday's talk, at first, how to increase the beam efficiency at the receiver in front. And next, we would like to how to control the beam direction by the phased array antenna in the afternoon. And at last, today, how to detect the target position. This is today's contents. So this is a brief introduction. As I mentioned yesterday, we've already published ITUR report about the radiative WPT. And in this report, it includes all WPT application from the wide beam WPT and the narrow beam WPT. And historically, as I mentioned, Nikola Tesla carried out the similar to the wide beam WPT. Of course, that's not his aim, but as a result of the low frequency in the end of the 19th century, he failed because he could not focus the wireless power beam to one user. And in 60s, William Brown used a higher frequency microwave, and he can focus the microwave into one point, and it is named the narrow beam WPT. It includes a solar power satellite. And we can but both WPT system and the wireless communication system and the other system, we use the same radio waves. It's the same. So why these systems are different names? So it depends on the wave theory. So I'd like to explain in the next. So as I mentioned now, we can classify the narrow beam and the wide beam. Additionally, Professor Khan mentioned in the previous talk, energy harvesting is one of the wide beam technology. Difference between the wide beam and the energy harvesting is the existence of the energy source itself. For the wide beam WPT, we must put a special transmitter. But for energy harvesting, we use ambient radio wave for Wi-Fi, for TV, or the other. So we categorize wide beam and energy harvesting are the same WPT system as a wide beam WPT. And this is the most important figure in my talk today. So this is a category of the field of antenna by distance. Usually, you use your mobile phone or Wi-Fi or PC at the far field, far region. In this region, the distance between transmitter and receiver is very, very long. So as I mentioned yesterday, originally by the Maxwell's equation, radio wave is expanded omnidirectionally at first. This is a real result of the Maxwell's equation. But when distance between transmitter and receiver is longer. And this sphere wave can be assumed as a plane wave. So in this distance far field or Fraunhofer far region, this originally sphere wave can be assumed as a plane wave. So this is a usual distance for Wi-Fi or mobile phone or the other. So I suppose you've already learned the technology of the wave propagation in this far field region. So I'd like to start my talk from this usual region of the assumed plane wave from far field. So it's the same as the wireless communications. So as I mentioned now, originally sphere wave, but this sphere wave can be considered as a plane wave if the distance is very large at a very far distance. So this Friis transmission formula is calculated by this equation. As mentioned yesterday, so originally this 4 pi d square indicate the area of the surface of the sphere itself. And we multiply the antenna gain and receiving aperture area and additionally transmitting power. So this is the original Friis transmission formula, and when we know this transmission formula, it's easy to estimate the received power at far field only. And here you can see we have a relationship between the antenna aperture area and the antenna gain with wavelength lambda and 4 pi. And with this formula, we can convert this original Friis transmission formula to these formulas. So, and we change this Friis transmission formula via these formula, and at last we get this formula at last. And sometimes professors in the wireless communication researcher put this formula is L means loss factor. But as I mentioned yesterday, again and again, this formula is not a loss. This is just a diffusion only. So there is no real loss in this Friis transmission formula. So please don't confuse. This is a loss, but loss by distance, diffusion or expansion of the radio waves. So if it's a rainy day or in the lossy medium, there is a loss, but this loss doesn't involve this loss factor L. So please don't confuse. And from this Friis transmission formula in far field, it's easy to calculate the energy beam efficiency ratio of the transmitting power and receiving power. It's very simple. So it's easy to estimate the beam efficiency at far field. But it's easy to understand when we increase the receiving area, when we increase the antenna gain of the receiver, we can multiply the receiving power or beam efficiency by this equation. But it's easy to understand when we put the 10 times larger gain antenna as a receiver, we receive the 10 times larger power, and the efficiency becomes 10 times larger. But as I mentioned again, in this Friis transmission formula, we assume the plane wave. This is most important point today. So if you are in the laboratory of the wireless communication, of course, it's easy to use this Friis transmission formula. There is no doubt. But please remind, it involves the assumption of the plane wave, long distance. So in this wide beam WPT application, the energy harvest application is an example in Japan, in Kyoto University. So, for example, this is a collaborative experiment with Panasonic and Kyoto University. We put a transmitter there, like a Wi-Fi based station, and we provide the wireless power everywhere in the room. So this wide beam WPT system is very close to Wi-Fi itself. It's a far field WPT system and a wide beam WPT system. And if we don't put any special transmitter, and instead of the special transmitter, we can use, for example, TV tower for the TV broadcasting radio wave. And this is one example of the experiment by the University of Tokyo, not Kyoto, Tokyo and the Georgia Institute of Technology. They gather the ambient radio wave from TV tower, and they drive very small powered sensor. This is an energy harvesting system in far field. So these are applications. And based on this phase transmission formula, we have to consider how to increase the beam efficiency. This there is no doubt in this equation. I mentioned again and again. It means here you have only 2 or 3 parameters only. Of course, 2 or 4 parameters only. So distance d, it depends on the distance between the transmitter and the receiver. And aperture area of the antenna for transmitting antenna to the receiving antenna. So if we have a larger antenna, we can increase the efficiency, or we can increase the received power. It's very simple. And this is the most important, lambda. Lambda means wavelengths, and if this lambda becomes shorter, smaller, it means the frequency becomes higher. We can increase the beam efficiency because lambda is here. So only the way how to increase the beam efficiency in far field, there is no doubt. We have only the 3 ways. We put a receiver in very short distance. Of course, we have to put the far field. And we must use larger antenna. But unfortunately, we need the larger antenna what we see in the even in the microwave frequency. And most important, we can when we increase the frequency, at last we can increase the beam efficiency or the receiving power. That's all how to increase the beam efficiency in this case. But here you can see there we have the other way how to increase the beam efficiency. But now I'm explaining the beam efficiency in far field. So in far field, there is no doubt. We have only the 3 ways. We put the receiver at a shorter distance, and we must put the larger antenna, or we should increase our frequency. That's all in this area. So for example, if we put the larger antenna, but if we request the 1 meter antenna as a business, we cannot do it. For the business or for users, we need a very small antenna. But based on this phase transmission formula, we need a larger antenna. So we need a super gain antenna, but I discuss a lot with antenna professors in the world, except Yagiuda antenna, very special antenna by Japanese. There is no super gain antenna. Small real aperture, but large effective aperture. So it's unfortunate. Based on this phase transmission formula in far field, we need a super gain antenna, but in the real, we must put a very large size antenna only. So next method is short distance. It means we have to consider the WPT in radiative near field. This, if we put a receiver in a shorter distance, this area is named the radiative near field here. And the border between the radiative near field and the far field is described as this formula. Yeah, so it depends on the wavelengths and diameter of the antennas. And this in this border, we can assume the plane wave over this border, and before this border, we cannot assume the plane wave, and we have to consider the sphere wave. So in this area, for example, this is one example in my PhD thesis time, so about 35 years ago. So this is a real measurement data at the radiative near field distance. In this case, we used a parabolic antenna as a transmitting antenna, and its diameter was 3 meters, and wavelength was 12 centimeters. We used 2.45 gigahertz, and we estimated the border between the far field and the radiative near field is, in this case, about 150 meters. And we put the receiver at 42 meters. It means this receiver here, rectangle, was in the radiative near field, and I measured this power density in front of the receiver by myself. And here you can see this is a power density contour. At the center, power density was enough. But if we change the position at the surface of the receiver, power density suddenly decreases. So in this case, there is no plane wave. This is measurement data by sphere wave. So please imagine when we use Friis transmission formula. At first, for example, we put a small receiver here, and we can estimate the received power by the Friis transmission formula. But next, we change the aperture of the receiver, for example, 10 times larger, from this small area to large area, 10 times larger. Unfortunately, if we have a 10 times larger aperture antenna, received power cannot become 10 times larger, because power density is not equal, unified. So we cannot apply the Friis transmission formula in this case. So we have to consider how to estimate the beam efficiency in radiative near field. But before going to the estimation, I would like to introduce how to use this short distance radiative WPT. For example, this is one example by Kyoto University and Mitsubishi Heavy Industry about 10 years ago. We proposed the automatic wireless charger for the electrical bicycle. And the distance was very short, because in this case, we would like to charge this electric bicycle over 100 watts, and we need a high power and we need a high efficiency. So we put a very short distance system. And this is a movie of this wireless charger. Sorry, in Japanese. Wait. So this is a transmitter, and this is a receiver. There you cannot see any antenna, but inside of this whiteboard, there was a wireless transmitting antenna. So automatically, between this distance, we automatically charge this electric bicycle. So this is one example of the wireless charger at a very short distance. But I suppose you consider it's very similar to the coupling WPT, like a mobile phone wireless charger. If we put a short distance, there is no difference between the inductive WPT and radiative WPT. So this is, I think this is one good approach to keep the high efficiency by the radiative WPT system. But we have to consider the convenience, how to change the distance when we use the wireless power only. So we Kyoto University propose the other system. Of course, usually we put the transmitter at a far distance. But when we need a wireless power, for example, in the emergency time, for example, on the mountain, some victim, it's unfortunate, but some victim dig under the snow or under the ground, for example. We would like to find him. But he has, for example, a beacon signal source. But for a long time, he is deep under the snow. Unfortunately, battery will be short, and this victim cannot transmit the beacon signal. At that time, we bring transmitter to very close area over the victim. Of course, we don't know where he is, but we transmit wireless power at a closed distance, and this victim or this beacon signal transmitter receive the enough microwave power, and this beacon signal arrives, and we can find him, for example. And this is one example of the experiment in an echo chamber. This is a drone with a transmitter, not receiver. And this drone brings the transmitter at a short distance, and here we put the beacon signal source. And now, please believe me, here was a microwave beam, and we can drive this beacon signal source without any battery. So this is one example how to be a short WPT system with convenience. So this is one proposal from Kyoto University. And so, as I mentioned, we cannot apply the Friis transmission formula in this case. So instead of the Friis transmission formula here, here is the original Friis transmission formula, and we put this parameter into the tau square. And with help of this tau square, instead of the Friis transmission formula itself, we must use this formula to estimate, to calculate the beam efficiency in radiative near field. So this is the x-axis indicates tau parameters. And if tau is large, it means distance is very short. Here, you can see distance is here. So, and tau is small, it means it's very far distance, And when we put the receiver at a very far distance, in far field, there is no difference between the original Friis transmission formula and exact Friis transmission formula here around there. But the efficiency is very poor. And when we put the receiver in very short distance, by the transmission, Friis transmission formula only, unfortunately, efficiency over the 100%. It's not natural because we use the assumption of the plane wave in this Friis transmission formula under the sphere wave condition. So instead of Friis transmission formula, we must use this formula, and by this equation, efficiency close to 100%, even if distance is very close. So I recommend you to use this formula instead of the Friis transmission formula. Even if distance is very far, like a wireless communication system, result is the same. So this is a real transmission formula without any assumption. So this is a formula of the efficiency in each distances. And we compare the beam efficiency and inductive WPT efficiency. Of course, we have to consider the size of the antenna, etc. But we pick up the typical parameters, the inductive resonance coupling and the radiative WPT. And based on this formula, we can keep very high efficiency with a 1 meter antenna both for transmitter and receiver, and the frequency is 5.8 GHz. And compared to the this radiative WPT, inductive WPT efficiency of the inductive WPT suddenly decreases. So I think, of course, we have to consider the size of the antenna of the system, but simply speaking, someone you consider inductive WPT has a very good efficiency, but radiative WPT has a very poor efficiency. But it's right. It's not correct. So if we choose an optical parameter, where we can keep a high efficiency at a long distance or very near distance. But if we cross the distance of the transmitter and receiver into very short distance, this field of the antenna changes to the reactive near field area. It means both antennas will be coupled electromagnetically, like inductive WPT. So please remember, Miyagi-Uda antenna use a coupling phenomena. So in this area, what happened? I introduced our experience. So about 20 years ago, we developed a wireless charger for the electric vehicle from the road to the bottom of the EV. And the distance between transmitter on the road and receiver at the body about 1 lambda. We used 2.45 gigahertz. So it's a very close distance. What happened in this experiment? So this is estimated beam efficiency by change of the distance between transmitting antenna and the receiving antenna. Here you can see there is no smooth degrees figure. There is a perturbation of the efficiency. It means when we put the receiver at the best position of the electromagnetic phenomena, impedance keeps the optimum impedance, and frequency does not change. So this area, it's the best parameters WPT, WPTs. But this area, to both antenna are coupled electromagnetically. As a result, impedance or resonance frequency changes, and efficiency suddenly decreases. So this is evidence of the electromagnetic coupling, like inductive coupling. So on Friday, I will introduce this total theory from the inductive WPT to the radiative WPT. When we use the same coil, sometimes we can consider this coil as a loop antenna. And when we use a dipole antenna for radiative WPT, but when we put this two dipole antenna in very short distance, this dipole antenna becomes electromagnetically coupled resonator. I will introduce on Friday in this total theory. But this is a beam efficiency classification in the radiative WPT system. And especially I focus on the radiative near field distance WPT system, how to increase the beam efficiency. Here, I introduced a very simple way how to increase the efficiency based on the phase transmission formula. But we have the other technology method to increase the beam efficiency. Of course, as I mentioned again and again, we cannot overcome the Maxwell's equation and the phase transmission formula. But based on the Maxwell's equation, as an engineer, we can increase the beam efficiency a little by this method. First of all, we have to consider the way how to increase the frequency. And in this number one column, it's the same way. When we change the distance, we can increase the efficiency, and when we increase the frequency, we can increase the efficiency. But for example, this is one example by Kyoto University, and we've already developed a 28 gigahertz to increase the beam efficiency, for example. But problem is here. So for antenna, when we increase the frequency, beam efficiency becomes higher, as I mentioned again and again. And if we consider the same efficiency, we can reduce the size of the antenna. So in this two point, so higher frequency is best to increase the beam efficiency. But phased array antenna beam controlling circuit becomes poor if we increase the frequency, and diffraction or the loss in atmosphere becomes worse when we increase the efficiency. And additionally, this is the most important point: circuit. Circuit parameters, efficiency, power decreases by increase of the frequency. Of course, device is the same. So we have a pros and cons in the higher frequency system. As an antenna, it's best, but as a circuit, it's worse. So, but as I mentioned again and again and again, we cannot overcome the maximization and the phase transmission formula. But as an engineer, we can expect the new circuit or new semiconductor at a higher frequency. So I recommend you to use higher frequency system, and we should develop higher frequency WPT system in near future with expectation of the technology. So this is a current example data of the circuit conversion efficiency of the rectifier. When frequency is very small, efficiency, circuit conversion efficiency is very high, close to 90%. But at 100, for example, around the 100 gigahertz, efficiency decreases. But maybe year by year, this trend becomes changed, and we can expect the higher efficiency rectifier transmitter in near future. So, but this is a general trend of the circuit, circuit parameter, the efficiency. Please remember it. And from here, I would like to, we should fight the maximization. And first of all, it's the easiest way to increase our little beam efficiency by the amplitude tapering technology with a flat phase. So basically, it's easy to estimate the beam pattern at the far field by the Fourier transmission formula of the transmitting antenna power density. And when we put the uniform power density at the transmitter, this uniform shape can be transformed by Fourier transform, and this is obtained beam pattern. So this means if we change the power density at the transmitter, we can change the beam form at the receiver. So based on this technology, we can change the electric field in the far field. So this is a famous amplitude tapering. We have some way named tapering, but this Gaussian tapering is most famous technology. And based on this Gauss formula, we can create this amplitude tapering as a transmitter. We assume the plane aperture antenna. And as a result, we get this waveform. Of course, now you cannot understand this is a good waveform or not. So I would like to compare the beam form between the power source from the uniform pattern and Gaussian beam pattern. So this black line indicates the waveform by the uniform normal aperture antenna. And we normalize the front gain. And if we adopt Gaussian beam, here you can see top gain, front gain decreases, but main beam becomes fat. So for the wireless communication researcher, this decrease of the front gain is not good, because wireless communication researcher, usually consider the front gain only. they do not consider the receiver area. They consider the antenna is only a 1 point. But we, WPT researchers, consider we must gather the radiated power on the plane. So if front gain decrease, but main beam becomes fat, it's better for a wireless power transmission system, because we gather almost all power in the main lobes. And of course, additionally, side lobe decreases. So side lobe power side lobe power move to the main lobe. So this is a comparison between the normal beam and beam by the Gaussian taper. So small front gain but fat beam and low side lobe. It's a characteristic of the Gaussian taper power beam, and efficiency becomes higher. And this is a simulation result by HFSS, electromagnetic computer simulation. And this is a theoretical beam efficiency without any electromagnetic coupling. And this is efficiency by the uniform transmitting antenna by change of the distance. And this red line indicates the efficiency by Gaussian taper. Here you can see efficiency becomes a little bit higher. So this is one evidence. If we can apply the amplitude tapering, we can increase the beam efficiency at a radiative near field distance. And here you can see efficiency decreases. This is evidence of the electromagnetic coupling. So this is a very interesting evidence and simulation result to increase the beam efficiency by amplitude tapering. And we have the other way. When we consider the Gaussian taper, of course, in the maximization of phase transmission formula, there is no problem. But in the circuit, we must put the different power sources. So at the center, for example, we must put, for example, 10-watt power source. But around there, at the edge of the transmitter, we must put a 1-watt power source or 0.1-watt power source. So if we create the uniform transmitting antenna, we put the same transmitter, same powered transmitter only. But when we would like to create a Gaussian taper, we must put very various transmitters in each area. So for the circuit, it's very complex system. It's not better. So we, Kyoto University, consider instead of the amplitude tapering, we would like to apply the phase optimization with a flat amplitude. So this is an optimized result by the phase optimization with a flat amplitude. It's very unclear, but black is a uniform. Here you can see higher side lobe, and blue is a beam formed by the optimized phase with a very low side lobes. And as a result, beam efficiency increases. And this is phase data in each areas of the transmitting antenna. We use the optimization method by the genetic algorithm. And as a result, if we add these phase in each antennas in each area of the transmitter, we can increase the beam efficiency here. But why this effect occurs? We consider this is a very close data of the phase distribution. And at the center of the transmitting antenna, phase is almost zero. It's the same. And when we move to the edge, phase is becomes minus plus minus plus. So it's not unclear, but this is not a two divided way. This is a one-dimensional array, and this indicates minus plus, minus plus, minus plus, etc. So please consider two sets of each antenna. At the edge, at the center, there is no difference of the phase. So it means these two antennas consider the same powered antenna only. But when we move to the edge, plus and minus phase is one set. It means plus, for example, plus 32 and minus 40. When we consider these two antenna into one antenna, plus minus phase combined approximately the zero power. So plus and minus, when we add the plus and minus phase, so amplitude becomes very small. So it means at the center, we keep the same power. But when we move to the edge, power from the two set antenna becomes smaller. It means by change of the phase combination, we can create the very similar amplitude tapering result. So this is our recent result. In this case, we should put the phase control system only. Amplifier or the generator, we can apply the same amplifier in each area of the transmitting antenna. So we propose this is a better way to increase the beam efficiency in consideration of the circuit contribution. So this is our Kyoto University proposal. And recently, we Kyoto University consider how to not only how to increase the beam efficiency, but also how to increase the total efficiency from the electricity to the electricity via microwave. So when we consider the total efficiency, especially in the radiative near field, we have to consider this tapered beamform at the receiver and this rectangular characteristic. Maybe as you know, rectangle has a peak conversion efficiency at the optimum input power. And when input power is become larger or smaller with the same circuit, efficiency degraded. And when we put the same rectangle in each area, at the edge, we can keep a high conversion efficiency, but at the edge, when we put the same rectifier, efficiency degraded. So in this meaning, if we consider the circuit efficiency of the receiver, this beamform at the radiative near field is not best. Not best. This is not good beamform for the circuit. So we consider how to keep the total beam efficiency. So we propose uniform beam density, even at the radiative near field. Of course, when we put the receiver at the far field, we can, as I mentioned, we can assume the plane wave and power density at the far field everywhere is the same. But in the near field, usually we have a peak and we have a power distribution at the receiver at the radiative near field. So we propose this uniform flat beam even at the radiative near field. Of course, we need optimization method by genetic algorithm or the other artificial intelligence, etc. In this case, we use Woodward-Lawson method. It is named a very famous method. And we combine the difficult beamform into one, and as a result, we can create the uniform flat beam at the radiative near field. And this is one example, and we get this uniform beam at the radiative near field. Of course, beam efficiency in a little bit poorer, a little bit smaller than the normal distributed power. But as a result of the combine of the total efficiency in consideration of the circuit, we can increase the total beam efficiency by this flat top beam at the radiative near field. So additional, I'd like to introduce two additional technology, not only in the radiative near field distance, but also the all distance. And it's the easiest way to increase the efficiency is to use multipath reflection from the walls. So, for example, about 15 years ago, we Kyoto University carried out an experiment of the WPT inside the car bodies. So, inside the car body means around the transmitter and receiver, there are a lot of walls for reflection. So this is a simulation result inside the car engine box. And we put the transmitter, we put the receiver around there, and by the multiple reflection, we can receive the more power compared to the one directional beam. And this is the result. When we consider the one-to-one only one beam, efficiency is there. But when we consider the multipath, we can increase the beam efficiency, double, triple, etc. So this is a very interesting technology to increase beam efficiency by the multipath application. And yesterday, as I mentioned, in the room, we can apply the same technology. We can avoid the human body, and we can increase the beam efficiency by the reflection. So here you can see we can increase the beam efficiency. So this is one example how to increase the beam efficiency by multipath application. And additionally, some of you know metasurface. It's most expected technology for antennas. So meta indicates the beyond. So when we develop this meta surface with the help of the resonator, we can overcome the natural material. So this is a very interesting application by optical region invisible flow. So when we put the meta material around the body, around the Harry Potter, this ray path of the optical ray path change to the unexpected degrees. So this invisible flow is the most hopeful technology for the meta material. And in the microwave region, it's easy to understand. We can control the beam direction based on the max resolution. We can change the medium parameter. Epsilon becomes minus, or the mu becomes a minus. So as a result, usually based on the Snell's law, propagated power is diffused to the outside. But when we put the metasurface sphere, this radio wave move to the other way, and we can concentrate on power. So this is an expectation to the metasurface, but we have two problems. When we put a large metasurface in front of the antenna, of course, antenna becomes small. But at the last, we have to combine the small antenna and a large metasurface. It means it's the same. If we consider the antenna with a metasurface, aperture area is the same, large antenna itself. And additionally, there are very high loss in metasurface. So, of course, in near future, we can expect a metasurface, but there is some problem now, especially this. At last, we need a metasurface, real metasurface with a small antenna. It's not good, I think so. So it's time to close. So today I would like to introduce how to increase the beam efficiency, and we have several ways. But unfortunately, we have to keep the max resolution and frequency transmission formula. But as an engineer, we have some way to increase the little beam efficiency, and sometimes in consideration of the efficiency of the rectifier circuit, we have some way to increase the total efficiency. So that's all my today's talk. Thank you so much. There is no chair, so do you have any question? And in this talk, we assume we put the receiver just in front of the transmitter, as I mentioned again. So this is the optimum or the optimum situation. But for the radiative WPT, so user will move to somewhere. So in this afternoon, I'd like to introduce how to control the beam direction. If not, yes, please. はいはい。あれはいはい。はい。
Hello. Sir, which system is better for smart home IoT application? RF energy harvesting or wireless power transfer?
Sorry?
Sir, for smart home IoT application, which one is better, RF energy harvesting or wireless power transfer?
Hopefully, energy harvester is better because we don't need any special transmitter. But there is a big problem on the energy harvester because we cannot control the power density at the receiver. Source is TV tower or Wi-Fi or the other. It means if we need more power to drive the sensor or the other, if we adopt the energy harvester, unfortunately, only the way to increase the received power is to develop the large size of the antenna only. But when we apply wireless power transfer, even in the far field WPT, when we user request a higher power and user don't require larger antenna, they only apply the small antenna, we can increase the transmitting power in the WPT system. So it has a pros and cons. And of course, for the energy harvester, there is no legal problem. So because power source is permitted wireless communication radio waves. But for the wireless power transfer, as I mentioned yesterday, so we need a special regulation. So it has a pros and cons. But I like a wireless power transfer because we can control everything in this system.
Thank you, sir.
Thank you very much for delivering this second lecture of second day.
Thank you so much. See you later. Yes, sir. Yes, sir.